Well, let's continue our discussion in chapter 9. Last time we stopped at these slides and we mentioned that we defined the p-value equals 1/2 as the null hypothesis because it implies there is no difference in performance between the treatments. And then after that, we used R code and calculate what we call the descriptive significance level, which is 0.028. This is actually a very small number, which means you would choose to believe in two things. One of these two things, either you believe that brand A is indeed better, or you have to believe that something with a very low probability happens. Usually, the rule of thumb is if this number is smaller than 0.05 or 5%, we would reject null hypothesis. Namely, if this number is too small, we would agree that there is indeed a difference between the treatments, and so we would rather believe this is more likely the case in this case. On the other hand, in one of the quiz questions, and you will calculate the descriptive significance level, which will result in a relatively higher number. And if that's the case, then you would rather believe that this would imply the null hypothesis is reasonable, or in other words, we don't believe there is a strong difference between these two treatments, or in the particular context is the two chess players. All right, so now let's continue our discussion in chapter 9. Today we're going to look at hunting caps. And so here in this example, we'll be looking at comparison with ties. So when you go hunting, you want to choose a hunting cap that makes you more visible to other hunters for your own safety. So apparently, if you look at the picture, the one on the right would make more sense than the one on the left. The one on the left may be more useful during the war where you don't want to be discovered by your enemies. All right, so here is the comparison experiment. We would like to compare two different colors of hunting caps. One is yellow, one is red. And so basically what we want to do is we want to do some experiment. We ask people to look at outside window, and where there are two people, one with the yellow cap, one with the red cap, and then see if they can spot either one of these two people or both or neither. So here, the result of the experiment is like this. So you see here, we have 70 of them spotted both, and then 5 of them spotted red but not yellow, and then 15 spotted yellow but not red, and then 10 didn't spot either one of them. So there's a total of 100 people. Now, the question is, what can we conclude from the table? Well, there is a big difference between this example and the example we had before on the treatments. On the treatments, there is no ties, namely, for each of the treatment, for each of the individual, either treatment A is better or B is better. But here we have a lot of ties. I actually have 80 ties, because for 80 of those 100 individuals, for 80 out of 100, either they spotted both of them, or they didn't spot any one of them. So we can't really tell which had appears to be better by looking at the result from those 80 people. If there's a tie, the easiest thing for us to do is to just remove the ties, only consider those individuals where there's no tie. So here there is 15 individuals spotted yellow and versus 5 individuals spotted red only. So we only look at these 20 individuals. And again, we have a classical 15 versus 5 situation. And sorry about that. 15 versus 5. And then we're going to use the same R code as we used before, and we're going to compute the significance level, which is about 0.03, which is less than 0.05. So our conclusion is that the data seems to support that the yellow cap is better, is can easily be spotted by people. All right, there's some other examples like this. And for example, here we can divide people into groups and then test if vitamin C will be useful in preventing the common colds. And we'll give vitamin C to one group, and then we'll give placebo to the other group. and of course they don't know what they're taking. And then after certain days, and we'll test the result. So here, over the period of about 2 months, and about 26% of the vitamin C group and 18% of placebo group had no colds. So there seems to be a difference. The 26% versus 18%, there seems to be a difference. But is this difference big enough for you to believe that vitamin C is indeed useful? We'll develop some tool to look at that. So we are not done with this example yet, but we'll move on to another one. We'll come back to this example in just a couple of slides. And so here, if P1 is the true proportion of volunteers with no codes, and we have infinite many, suppose we have infinite many volunteers, and P2 be the corresponding true value, and for taking the placebos, and we want to know whether we want to believe P1 minus P2 is greater than 0, which means vitamin C is indeed useful, or P1 minus P2 is less than or equal to 0. This would mean that vitamin C either has no use, or maybe it is actually even worse. So because we don't have infinite sample, this is only theoretically possible. So we want to approximate P1 and P2 by P1 bar, which is 26%, and to P2 bar, which is 18%. We'll learn how to compare whether this difference is big enough or not soon. So here, whenever there is a 2 by 2 table, have equal value P, that is P1 equals P2, and then we say that there is no association between the two attributes being studied. And then we say that attributes are independent. If the P's are unequal, we say that they are associated. We say that they're independent. And what we found in the vitamin C example and is that we suppose there is association between the treatment given and also the successful rate in avoiding the colds. So let's take a look at this example. Suppose we want to study two attributes, A and B. So we have a total of about 2,000 people, and we divided, we just test them whether they have A or not, whether they have B or not. So we end up with this table like this. So you see here, there will be 100 people having both A and B, 300 having not A but B, 400 not B but A, and 1,200 having neither A nor B. Now, we would like to find out whether A and B are independent. Well, if you look at A group, if you look at first column only, let's look at the first column. What you can find out is among this A group, 1 out of 5 of them has a B. Or in other words, the ratio between B and non-B is 1 to 4. And notice that this is the same for the non-A group. It's 300 out of 1,500. And the ratio between B and non-B is also 300 over 1,200, which is also 1 over 4. Well, what we want to conclude from this example is that in this particular example, the A group and non-A group have the same percentage of Bs. The A group and non-A group has exactly the same percentage of Bs. Or in other words, whether you have A or not does not increase or decrease your probability of getting a B. So what this tells us is that A and B are independent, and B are independent. Whether you are in A group or not A group, you have exactly the same percentage of B. So here, when we test for the equality, for true B such tables, we're testing for the lack of association. Or in other words, we're testing whether A and B are independent. In this particular example, for these particular numbers, our conclusion is that A and B are independent. And if you test the hunting caps, and you like to test whether the ability of spotting yellow is independent or dependent from the ability of spotting red. And notice that here we're not comparing yellow and red. We're not comparing them which one's better anymore. We're doing a different comparison. We're comparing whether it is the ability to spot red is independent or dependent of the ability to spot the yellow. Well, notice that. So you see here, for those people, for those 85 people who spotted yellow, and 70 of them actually spotted red also. So here, the percentage of those people who spotted red in this group is about 82.3%. On the other hand, for the people not spotted yellow, the percentage is 5 out of 15, which is about 33%. So you see there is a big difference between the percentages, which tells you that this is a strong evidence supporting dependence, namely the person's ability to spot in yellow is dependent of the person's ability to spot red. And so the question is the rate of spotting red associated with the outcome of yellow? The answer is yes, because we observe a big difference in the percentages. In practice, it's almost always the case that you will observe some difference. And how big is difference big enough? We'll explain this in the next video. But for now, this would be big enough for us to conclude that they are dependent. And hypothetically, if they were independent, then the ratio, the numbers would be more like this. So for example, if hypothetically we modify the numbers to this new table, and then among the yellow group, we have 68 out of 85, which is 80%. That's the same as this group, which is 12 out of 15, which is also 80%. So this will be a hypothetical independent case where the ability of spotting yellow is independent of the ability of spotting red. So here the independence tells us that if the row proportions are independent of columns, then the column proportions are also independent of rows. So this is also true. For example, if you look at the first row, and among those people who can spot red, 68 out of 80 of them can spot red also. So this answer is 85. And if you look at the second row, 17, this is the people who didn't spot red, and the 17 out of 20 of them, which is also 85%, can spot yellow. So the rows and the columns are independent at the same time. Now let's talk in a little bit about the finding the missing numbers in the cells of the tables. Suppose you have a table like this. If we have independence and we know and how the rows and the column totals, what number should be expected in the cells of the 2x2 table. So suppose that we assume that there is an independence. Let me actually open the table, the whiteboard, and or actually I can do it here. Suppose that you have independence, and then what you can do is to, assuming that they're independence, then we can find its missing values. So here is how it works. So let's say for the first row, which is the B group, and we want to find out how many people has A and how many people has not A. You see here, the total A's is C out of N. So here, the percentage of A should be C over N. So C over N is the percentage, C over N. So the first group should give you the probability right here. This missing number is, well, you have a total of R, so it should be R times C over N. Actually, I'm having a little bit kind of join. I will just use the type thing, and I'll just type it. This number here should be R times C over N. So this is the first missing number right here. And then the second one, of course, will be R minus this number, RC over N. So this is the second missing number. The third one will be C minus RC over N, because the total for these two entries would be C. And of course, the fourth one, I've run out of space. You can also use the subtraction, use N minus C minus that number. So this number right here, the fourth missing number, I will just use N minus C minus R minus RC over N. And this simplifies to N minus C minus R and plus RC over N. So that would be your fourth number that's fits in here. So if we're assuming independence, then we can theoretically figure out what those numbers are. All right, and of course we would expect the samples to the percentage fluctuate a little bit. For example, here the expected count, if we assume the vitamin C and placebo has nothing to do with preventing cold or not. This is the ideal. The second table is the ideal outcome. You see here in the first row of the second table, this is the same number, 88 versus 88. So you see here we have exactly 1/2 of for no cold group, 1/2 have been took with vitamin C, 1/2 didn't, and similarly for the cold group. Or you can also look at the vitamin C group and placebo group. They have exactly the same percentage of people who got cold and who didn't. But the actual number we observe will be different. The actual number we observe will be something like these. And now these tables are different. For sure, they are very different. Now the question is, do we want to interpret this difference as a natural fluctuation of the measurements, or do we conclude that there is a real difference? And this will lead to our next topic called chi-square test, which I will cover in the next video. For now, thank you so much for watching. I will see you in the next video.